My name is James Johns. I'm staff scientist at PHI, and this is the second part in an ongoing series about how to use tools on multi-purpose XPS instruments to not just acquire information about the atomic composition of surfaces, but to actually measure the electronic structure. And in particular, we're focusing on reals, UPS, and LEIPS. These are three common techniques that are used to get information about the valence band and the conduction band structure. We talked about these three techniques and how to think about them in the previous section of this video, the previous section of the series. So if you haven't seen that, I encourage you to go ahead and watch that on our YouTube channel. Because in this series, we're not going to talk too much about the theory behind them or how the experiments work, but instead we're going to talk about some more practical advice about how you can reliably get the best information possible for the materials that you're trying to measure. So with that, let's go ahead and get started. Okay, so an outline for this talk is pretty straightforward. The first is we are going to have a very quick overview, just to make sure that we're all using the same terminology and understand what the experiments are. Not going to go into them in depth here, but I want to make sure that we're all on the same page. Then we're going to talk about the challenges with each of these techniques. And in particular, we're going to address the things that are most likely to cause an experiment to either fail or to give data that is incorrect. And that's certainly something that we want to avoid. And then finally, we're going to talk about how we can overcome these. And this is going to be things about you can do before you do your experiment, things that you can do during your measurement, and then once your measurement is done, how do you know if it was good or not? So how can you distinguish good data from bad? So that's going to be the plan for this talk. Okay, so just a quick refresher. When we're talking about the band diagrams or the band structure information in our system, these are the things that we're looking for with these three techniques. We have a valence band that has electrons occupying it. They go up to the sort of valence band maximum or a HOMO type level. We have unoccupied states that you can put electrons into. And the things that we're going to directly measure are the Fermi energy. And that's just the energy level that separates the occupied from the unoccupied electronic states. The vacuum energy up here, and this is the energy of an electron at rest just outside the surface. The work function, which is defined as the energy difference between the vacuum level and the Fermi level. The ionization energy, or the ionization potential, this is the difference in energy between the vacuum level and the top of the valence band, or the valence band maximum. The electron affinity, which is the energy difference between the vacuum level and the bottom of your conduction band. That's the energy released when a surface gets an electron. The electronic gap, which is the energy difference between the conduction band, between the bottom of the conduction band and the top of the valence band. And the optical gap, which is the minimum energy required to excite an electron in the system, but neutrally. So we're going to have an electron and then a hole that gets left behind. And this is what we measure with reals. Okay, so with LEIPS, pretty straightforward experiment. We're going to start with an electron beam that's hitting the sample at fixed energy. And we're going to be detecting a photon at an energy h nu. We're then going to apply a sample bias that's going to slow the electrons down. And at some point, we're not going to get those photons anymore. And then we're not going to get the electrons getting into our sample anymore. And if we look at the energy difference between those, the point where we stop getting electrons in, which is going to be our LEIT inflection point, and the point at which we stop getting LEIPS signal or photons out, and we compare that to our band, to the energy of the photons that we're looking at, we get the electron affinity. Next, we have UPS. UPS is very similar to traditional X-ray photoemission, but instead of using X-rays, we use UV light. And now 99% of UPS experiments are going to be done with helium. It has two energy photons that you can use. It has a 21.22 EV photon and a 40.8 EV photon. And this is going to give us information about the valence band structure. So when we take a UPS spectrum, we're going to take a look over a binding range, a binding energy range. It's relatively small and with high resolution. And in order to get all the information we need, we will also need to apply a small bias to the sample to force the electrons into the analyzer when they come out with zero kinetic energy. And there are two particular regions that I want to pay attention to. The first is what we call the secondary electron cutoff. These are photoelectrons that are being emitted from deep within the valence band or low-lying core levels, and they're being emitted just to the vacuum level, so they come out with zero kinetic energy. And this is telling us about the vacuum level. And the next thing that we want to look at over here is the electrons that come up all the way at the top with our maximum kinetic energy near either the Fermi level or the valence band maximum, if those two are different, i.e. it's not a metal. And that will tell us about the valence band maximum. We can combine those two pieces of information to get the ionization potential. So the ionization potential is just going to be the photon energy we're using minus the energy difference between the front of our spectrum and the back of our spectrum. Easy peasy. And then finally, we have reals. And with reals, remember, we're shooting a beam of electrons with fixed kinetic energy into the sample, and we're looking at the electrons that get scattered away. Now, most of them get scattered away elastically with no change in energy, but some of them will excite an electron in the system into the conduction band, causing the scattered electron to have less energy than when it came in or have an energy loss. So here we have a real spectrum of hafnium oxide that's taken at with a 1 kV beam. We have here our elastic peak, which you can see quite clearly. And if we zoom in really far, we can see that we have some structure down in this bottom region. We have a region where there is effectively no signal, and then we start getting some scattered electrons again. And this region where we have the onset of the signal coming, this lost signal, is basically giving us the optical gap in our system. Okay, so those are the three techniques. Like I said, if you're not familiar with these, I highly encourage you to go back and watch the first video. But we want to start talking about some practical aspects. Okay, so these are some really powerful techniques, but if they're so great, why don't they get used more often? So I did a quick literature search and looked for papers with LEIPS, UPS, reals as keywords. I found about 4,000 looking at inverse photoemission, 6,000 with UPS. Reals, I only found about 1,000. With XPS, I found over 70,000, right? There's just more people doing XPS. Obviously, people want to know what the atomic composition of your surface is. And if you want to do one of these other techniques that measure the electronic structure, you probably need to start with knowing what the atomic composition is. But there's another reason why so many more people are doing XPS than these other techniques, and that's because they have challenges. And I'm going to start with the biggest one, and that's electrostatics. In both LEIPS and UPS, you have to measure electrons that have nearly zero kinetic energy, right? These are electrons at the vacuum level. Because that is an integral component to getting the ionization potential and the electron affinity. But measuring zero kinetic energy electrons is difficult. And the primary reason is that if you have an electron at rest, it's not moving, it's not doing anything, that means that if there is some charges nearby, or even not so nearby, the electron is going to have plenty of time to interact with them and change its energy and change where it's going, right? Remember that the potential for a point charge is proportional to -1 over the distance between them. That's a long-range force. And so that is a big problem, that the low-energy electrons are so sensitive to stray fields. Now, you might be thinking to yourself, well, okay, I'm not hooking these up to an electrical circuit or anything. Where are these stray fields coming from? And the answer is they come from a variety of different places. I'm going to talk about three main ones. The first is contact potential difference. The second is that when you do these experiments, you have charge building up during the analysis. And then the third is sample heterogeneity. And this can come from a variety of places. It can be sample defects or mixed samples, any number of things that make your sample less uniform. Okay, so let's start with a contact potential difference. A contact potential difference occurs when we have two materials that have different work functions, or a difference between their Fermi level and their vacuum level when they are separated. And then we bring them together and form an electrical circuit. Because when they're separated, then it turns out that what happens is their vacuum levels are going to align with each other, meaning that they have a difference in their Fermi levels. So there's a shift going between them. However, once we make an electrical circuit, we provide the flow of electrons between the two materials, charges will move until they equalize their Fermi level, because the Fermi level defines the difference between occupied and unoccupied states. As a result, the vacuum levels will no longer align, and this will cause there to be a potential difference that is felt by a charge traveling from one material into the other, which is basically the difference between their now relative vacuum levels. So anytime we have two materials with different work functions or different vacuum level, Fermi level energy differences, you're going to get an electric field at that interface. You might think, okay, well, my sample is just made of one material. I don't have to worry about that. And unfortunately, for low energy electrons, that's not quite true. So Hecken, Bleichener, and others did these really beautiful experiments where they looked at near threshold photoemission, so electrons being emitted near threshold with very little kinetic energy. And they looked at them sort of on the gold sample that was surrounded by a copper block. And one of the things they found is that they got very different photoemission yields when they put their UV beam in the middle of the beam, in the middle of the gold disc versus the edge. And the reason for that is the contact potential difference between the gold and the copper. It's around a 0.5, 0.6 EV difference between the local vacuum levels for copper and gold. So that's kind of disconcerting. And that's one of the reasons why we always want our samples to be somewhat large and homogeneous if we want to know what the band gap or the ionization potential or electron affinity is of a material. You can make a measurement when it's not just that material or nice and big and uniform. But then you have to realize that what you're taking a measurement on is the composite system, not the material just where your beam is hitting. And also, I said we don't apply electric, maybe you don't have an electric field, but to measure the secondary electron cutoff, we do have to apply an electric field. And these are some simulations that were done by Hellander and others that were where they looked at 10 EV electrons and quarter of an EV electrons in the presence of a small applied bias. I think it was like 15 volts. when the sample was normal to an energy analyzer, and when it was tilted away at 45 degrees. And you can see that when you're tilted, the electric field lines don't point directly into the analyzer anymore. They don't guide your electrons in there. And so these low energy electrons don't even make it to the analyzer. So not only do we want our sample to be uniform and large area, it's very important that the sample be perpendicular to any charged particles, so outgoing photoelectrons in UPS and incoming electrons in LEIPS when we're applying a bias. Okay. The second source of electrostatics being a problem here is sample charging. So this is a very simple diagram, right? You have your grounded sample holder, you have your sample, which maybe has some band gap to it, and you have current flow, right? If you're doing UPS, you have around a few nanoamps of photoelectron current. If you're doing LEIPS, you probably have closer to microamps of incoming electrons. And if you're doing reals, you're sending electrons in, you're scattering most of them, you effectively have net zero current, but you do end up getting with some transmission until things equilibrate. So with this current flow, if this sample isn't perfectly conducting, what's going to happen? Well, we're going to build up charges on it. Just like you have do an XPS, but unlike an XPS, we can't use neutralizers anymore because the neutralizers would alter and overwhelm any signal we had from our low energy electrons. So one thing that we can do is we can model an equivalent circuit diagram for our sample. Now, this is a paper from Sina and Showit. I really like this paper. I don't know these authors, but if you're having issues with charging in your experiment, I highly recommend going and taking a look at this paper because it's really well written. And basically what they do is they model the components of their system as equivalent circuit diagrams with resistors, capacitors, voltage sources, current flow, and a photodiode for the UV source. They were modeling this for UPS. The exact same diagram would apply for LEIPS, but instead of photons coming in, we have electrons. Okay, and they have a resistance and series and for the surface potential of the substrate. That creates a voltage at the dielectric and substrate interface. There's some capacitance to the dielectric. There's resistance between them, and then there's a resistance that's due to the surface dipole. And these things, importantly, are not necessarily the resistance of the material when you put a multimeter across them. These are the effective resistances of the sample under the experimental conditions, which can be quite different. In UPS, you have these UV photons, so you can get some photoconduction. In LEIPS, you also have photons being emitted from your sample, which can increase conductivity. So it's not necessarily what you would measure, and in LEIPS, you also have to think about that it's resistance of an electron in the conduction band, not necessarily the resistance of a hole traveling in the valence band, which can be quite different. So it's the resistances are of the experimental conditions. And what they look for is how can we model what the surface potential, this voltage right here at the surface of our insulator is, because that's what is effectively any voltage shift you would see in your experiment. And then importantly, because one last thing I want to point out, because this dielectric material needs to be modeled with some capacitance, because you're storing charge on one side and charge on the other, and that's just a parallel plate capacitor. That actually means that you have some time dependence to your sample. And if you've ever taken, say, XPS data on a system that's charging, you might notice that if you take it cycle after cycle, the band energy, or sorry, the peak energies are moving with each cycle, and that's because of this capacitance. So I think that's a really great paper, and I highly recommend reading it. But the final source of local electric fields is heterogeneity. So there are all sorts of ways that you can have heterogeneous electric fields. You can have heterogeneous electric fields that come from orientation of the surface dipole. The surface dipole is effectively what keeps electrons inside a material in a system, and is the dipole that exists outside of the surface between the vacuum and the electrostatic equilibrium in the bulk of a material, and it creates a dipole. And that dipole can be sensitive to how molecules with their own dipoles are oriented on the surface. So if you have molecules, or you can have molecules oriented so that the dipole of the molecule adds to the net dipole of the surface, or they can be oriented in the opposite direction, point away, and this is going to give you a different work function because you're changing the electric field present at the vacuum level. You can have surfaces with composite materials. This is a set of really great experiments where someone took hexadecane thiol and then a perfluorinated version of that. The perfluorinated version has a high work function when it's bound to gold. The hexadecane thiol has a low work function. And they made stripes and they mixed them together. And then they took UPS. And you might think, okay, if I have different stripes here, and say I have 50% of the low work function stripes and 50% of the high work function stripes, what I should get for my secondary electron cutoff is two peaks, one at the low work function and one at the high work function vacuum level. But in fact, when they look at the actual data, that's not what they see. They do see a little bit of a dip where the high work function material should be, and that's at roughly the correct energy. But the low work function material, the actual ensemble secondary electron cutoff energy for the system, is different from either one of those, and it's some mixture between them. And the reason it's not just this pure low work function secondary electron cutoff is because these electric fields are long range and they influence how the photoelectrons move when they come out with near zero kinetic energy. You can also get the same effect, but instead of having purposefully heterogeneous materials, if some of your material is clean and some of your material is dirty, adsorbates on the surface of a material can change the work function. If those adsorbates are only on part of your sample, so you have some patchy areas that are clean, some patchy areas that are dirty, then you'll get a ugly looking secondary electron cutoff. And so, or you can even have just different Miller planes, right? So if we take a look at these are some single metal crystals that have different surfaces exposed or different planes, and you can find that there's quite a bit of variation in what the work function is for a single material just based on what surface is showing. So silver is a common example and has a 0.4 EV difference between the 111 and the 110 work function. So if you have a foil, for example, which has multiple different faces presenting on the surface, like say a mixture of 111 and 100, you will get a little bit of broadening in your energy, and you'll get a work function that's somewhere different from either one. And then finally, and most importantly, I think to a lot of our audiences, you can think about that same effect now being applied to powders. So powders obviously have many different facets exposed. They typically have oxides on the surface and can be charged. And so what's being shown here is someone did an AFM experiment of this oxide nanostructured powder. And then they did Kelvin force microscopy, which gives you the local work function or the change in the contact potential difference on the end of a tip as it passes over the material. And you can see that there is over a volt of difference just in this powder. And that's very common for powders. It makes powders very difficult to analyze with UPS or LEIPS because you have such a broad distribution of local electric fields. Okay, so heterogeneity is another reason why we want our sample to be so uniform. If we want to know a material property of the material itself, then we actually need to have a nice big uniform sample because otherwise we'll have local electric fields that are messing with our vacuum level. But there are other sensitivities, not just the charging. One sensitivity is the surface sensitivity. So in XPS, we think of it as a surface sensitive experiment because it's sensitive to things that are happening in the first, say, 10 nanometers or so. And this is usually based on something called the universal curve of inelastic mean free path. So this is a very old concept in surface science. And this works very well on the high energy side. But in blue, what I have right here are the energies of electrons for UPS. And over here, we have the energy of electrons for LEIPS. And this low energy side is very material dependent. But it turns out that for LEIPS and UPS, we're typically sensitive to things happening in the first nanometer or so, right? So this means that we are often sensitive to small contamination on the surface because it changes the local dipole and electric fields. And we're sensitive to changes that might not even be visible under XPS. And to give an example of this, showing the evolution of the secondary electron cutoff in the valence band region of a UPS spectrum of silver, taken over time, over about 2 hours, in a chamber that has a background pressure of around 1 × 10⁻⁸. And you can see that the valence band structure here isn't really changing. However, the binding energy that the secondary electron cutoff occurs at is changing, and it's going to larger and larger binding energies as carbon-based contamination in that chamber are starting to be deposited on the surface and change the surface dipole, thus changing the vacuum energy level. And this secondary electron cutoff can be a really nice way, actually, to probe how clean your surface is and whether you're depositing stuff on your surface that you don't want to, because it can be more sensitive even than UPS. But the sensitivity means that if you want to look at a clean sample, because you want to get an accurate value of the ionization potential or the electron affinity, then you really need to have very good vacuum to keep stuff from depositing on the sample. Because it needs to be clean for the entire length of your experiment, or else that secondary electron cutoff, or in LEIPS, your LEIT inflection is going to be moving during your experiment. And then finally, the data analysis component is different than in standard XPS. It's not hard necessarily, but it is different, right? So there are a couple of things that can trip people up. For UPS, we have so many photons that come out of a normal UV lamp that once we apply bias to the sample and start accelerating them into the analyzer, we can have a ton of counts, right? So here we have UPS of gold surface with a 10 volt bias on the sample, and we have about 9, almost 10 million counts per second at that cutoff. And yet we only have about 40,000 over here at the Fermi level. So that can be a challenge because this is now so many counts per second that the MCPs actually can't keep up. And so it becomes not a linear representation because you don't have linearity in your intensity over that whole range. It can also be challenging if you have low intensity states. So states near the valence band maximum that can be caused by defects or in the gap can have a low intensity, and you need to be careful about that. So here I have an example. This is a UPS spectrum. You can see the intensity of these states near the valence band onset are really low. But that's not actually the valence band onset, because if I look at this binding energy, that's a negative binding energy of minus 11.844. And I will tell you that I'm applying a 10 volt bias to this, so I shouldn't have anything beyond 10. What is going on here? Well, it turns out when you do UPS with a helium lamp, you actually have satellite peaks. There are 2 satellite lines of helium-1 that have about 1.5 and 0.5% of the intensity of the helium line, of the helium-1 line. And so this onset right here is actually occurring over here, and this is the Fermi level of the gold surface that I was looking at. But if you are looking at things with sort of low density in the gap type states, you do need to be careful if they come up near the Fermi level, or even if they're not near the Fermi level, that you may need to take into account these sort of satellite peaks that can be there and subtract them out. And importantly, this was a major issue in the perovskite field. Very famously, people argued for a long time about the density of states in perovskites. And part of that came down to people not accurately accounting for these satellite peaks in their UPS spectra of methyl ammonium lead triiodide perovskites. Okay, so that's UPS. What about LEIPS? Well, with LEIPS, one of the biggest problems can be actually picking the inflection point. So in order to find the inflection point in the LEIP, what we do is we take the numerical derivative of the transmission current. But numerical derivatives are inherently somewhat noisy. So if you have any sort of wobbling or wiggling going on in your transmission current curve, you can get a derivative that has several different humps in it. Or if you just have some noise in your electron gun, you can get the same thing, right? So here we have a pretty simple example. This is LEIP from one sample, a very nice strong signal, relatively symmetric. It's a little double humped, but not too bad. And over on the right, we have a LEIP from a LEIPS measurement on a sample that had very low transmission current. And so it's much harder to get a clean derivative. And so how would you measure this? How would you pick where this should be? Is it at the very highest point in the spectrum? Is it sort of in the middle? Is it the first point that looks like it's reaching a maximum? And the best answer I think we can give is to actually take that one in the middle. What you want to do is look at when the total current is coming into your sample, and normally the left side of this curve will be more symmetric than the right. And so what I do is I put it right in the middle of where it would be if I just flipped this around and made a mirror of the left-hand side. And that will be usually a good value for the inflection point when you have something that's a little bit messier and you have to use your best judgment about where to put it. And finally, for reals, the largest problem with reals occurs when the elastic peak is broad. So if you're using a lab 6 filament, it's usually very simple to get the elastic peak under around 0.5 eV. With the tungsten filament, it can take a little bit more work. But either way, if you want to measure a lower bandgap material or look at hydrogen, the wings of this are going to overlap with the loss features that you're interested in. And so the best way to do this, to approach this, is actually to use curve fitting. So you can use curve fitting to fit the elastic peak to a Gaussian, subtract that, and then you're left with something that can give you the full area of your peak minus your background function for an elastic scattering. And that's what I would recommend in order to push reals as far as it can go towards low bandgap materials or hydrogen quantification. All right, so before we wrap things up, I just want to share a little bit of my practical experience that I have with these techniques and some ideas that you can set yourself up for success to get the best data possible when you're interested in getting a band structure measurement. So this is going to be primarily focused on UPS and LEIPS. Okay, so the first thing, which applies to all three techniques, is sample mounting. And the first thing that we want to do is we want to have a relatively large sample. This is less important for reals, but it's very important for UPS and LEIPS because you don't want to have contact potential differences between your sample and the sample holder, or sample and whatever you're making electrical contact with it. You want to have a nice big area, much larger than the actual measurement of the beam, because at that low kinetic energy, long-range forces will affect it. So we recommend ideally 1 centimeter by 1 centimeter. Next, what I would recommend is making electrical contact to the top surface from your platen. So here you can see I've made an image where we have our sample that we want to analyze, and I've used screws with washers to press it down into the platen. And importantly, and I've seen this happen before, you don't want to do this with just one side, because you don't want your sample to be sort of cantilevered up at a weird angle, because then you won't be perpendicular to the incoming electron beam or outgoing electron beam for UPS. And so your field, when you apply a bias, isn't going to be directly along the axis to the analyzer. So you want to keep it flat if at all possible. And sometimes this will still not be enough to get the job done. So what do? If you still see charging, then what I suggest doing, wrap the edges of the sample in foil to give sort of a large area contact. This changes your contact from being individual points to being lines or area, and that gives you a much lower resistance. And then finally, if that's insufficient to reduce charging in your sample, what I would suggest is to make your sample thin. So if you make your sample thin enough, on the order of 10 to 20 nanometers, you can measure just about any band gap material. And the reason for that is you will have sufficient sufficient transmission current from tunneling and Fowler-Nordheim tunneling, which is tunneling basically through thermally activated defect sites, to dissipate any trapped charges at your surface and prevent significant charging. So those are the steps that I recommend to minimize charging, and they can all be done by mounting the sample. The next thing that I'm going to point out is if you want to get the absolute energy position relative to the vacuum level or the Fermi level of your system, it's important that you're measuring the ionization potential and the electron affinity of your sample. That means not your sample with a bunch of advantageous carbon or your sample with an oxidized surface layer. You need to measure your actual sample. And that usually requires some form of cleaning. So, you can use a gas cluster ion beam is probably the best way to get rid of this. If you don't have a gas cluster ion beam, you can try a low voltage argon beam, but that is going to be more likely to damage your sample. And so the goal is to clean it with clusters to get something like this, where I have this sort of darkish brown layer on top to represent the advantageous carbon, and we remove that without damaging the layer under the material that we're interested in underneath. What you want to avoid is doing something like this, where you not only sputter off the carbon, but you start having sputter-induced damage inside your material. Now, because these techniques are so surface sensitive, it is possible to have sputter-induced damage or covalent junk attached to it that is too small to be easily seen in XPS, but can still affect your measurements. So if you're worried about surface contamination or whether you damage your surface, one way that I recommend checking for that is by doing your sputtering and checking for it, not with the XPS, but with the UPS instead. And looking at, is your secondary electron cutoff changing? And are you getting weird states popping up near the Fermi level, suggesting you have damaged your sample and have dangling bonds? And in fact, UPS is a great tool for monitoring surface contamination by doing that exact process. There is another option, though. If you have a material that gets too easily damaged by sputtering, one thing that you can do is to measure the LEIPS and the UPS of the system while it's still dirty. Now, that sounds a little counterintuitive because you're going to get wrong values for the electron affinity and the ionization potential. But what we will get is a band gap that is correct, because the surface contaminants largely will affect just the vacuum level by changing the surface dipole. It won't affect the energy separation between the unoccupied states and the occupied states. Then if you want to try and get those band edge alignments, what you can do is then try and clean the sample and perform UPS on the clean sample. and then apply a rigid shift to your bands to make that line up. The reason why this is sometimes a useful tool is that because LEIPS can take so long to acquire good signal, it can end up, you can start with a clean sample, and if your sample is somewhat reactive, you can end up with a slightly dirtier and contaminated sample happening during the time scale of your measurement. And so this is a way you can kind of get around that. This works really well for organics and molecular system where you have no dangling bonds on your surface, but it is absolutely not appropriate if you have a modified surface structure that's different from your bulk, like you have an oxide passivating layer, or you have a system that has dangling bonds on the surface and is going to be very reactive towards gases, then this isn't going to work out and give you the right answer. But it is an alternative strategy that you can try when you run into problems with trying to take UPS and LEIPS on your clean sample and keep it clean. And then finally, I just wanted to mention something, which is that reals actually usually doesn't need any particular cleaning. Because you're often using a beam energy that has a penetration depth that's much higher than the sampling depth for UPS and LEIPS, it is way less sensitive to surface contamination. So as long as your surface layer is smaller than roughly half the penetration depth of your electron beam for reals, and this is important, and your surface layer is a higher band gap layer than your bulk. Now, this is going to be true for mostly if you have like a bunch of adsorbed alkanes and hydrocarbons on the surface, they're very large band gaps. If you have an SiO2 layer on the surface, that's got a very large band gap. But if your surface is, if you do have a surface layer that's different from the bulk, and that surface layer has a smaller band gap, then this is not going to work out for you. You're going to have to remove that by sputter cleaning or cleaving or doing some other way of getting rid of that. Oh. And then I wanted to talk about charging, right? So let's talk about this in the context of LEIPS. And in LEIPS, I think people can often get a little bit confused because when you start a LEIPS experiment, you will often see your LEIT shifting energies for the first cycle or two. That's actually totally normal. Part of that, at least in our systems, is that because the sample is being used as the final electrode in our electron gun for LEIPS, there's actually a little bit of a electronic reorganization that happens there. And you're seeing the capacitance, all the trap charges fill up. And so you expect to see a little bit of shift. Now, this shift will be from low bias to high bias. So red is the first cycle here, and then the rest of them all line up. And that shift goes from low bias to high bias. When you have charging, you will still get a shift, but it will go in the opposite direction, right? And this makes sense. As you charge the electron, as you charge the surface up, that surface becomes negatively charged and adds an additional repelling force to the incoming electrons. And so you're able to completely shut off electrons being transmitted into the sample at a lower bias when your system charges up. So when your system starts charging, then you want to start thinking, do I need to remount my sample? Do I need to prepare it differently? Is there a different way I need to approach this? And the key hallmark of that is going to be your LEIT to moving to the right, moving to lower biases when you see your inflection point. Another thing that can commonly happen is using the wrong bandpass filter. So when you do LEIPS, your bandpass filter has to have a center photon wavelength with a larger, sorry, has to have a center photon energy larger than the electron affinity of your sample. So here's an example of some data where that sort of mistake was made. If you try and measure gold, which has a work function of 5.2 eV and it's a metal, so its work function is its electron affinity, with a 260 nanometer bandpass filter, which is our most commonly used filter for LEIPS, you will see that the LEIPS onset seems to be happening around 8.2 eV, but the LEIT inflection is all the way up here at 7.76. And so you're getting LEIPS all the way from this tail end here of this LEIT, and there's no separation between your LEIT and your LEIPS. When that happens, where the onset of your LEIPS is identical to your LEIT inflection or slightly lower, then you need to change your bandpass filter. That's how you can know. And you need to be looking at higher energy photons because your electron affinity is larger than the photon energy of your bandpass filter. And then finally, for UPS, I think this is the last example we're going to run through. One of the most common problems is surface contamination. UPS is really at that sweet spot on the universal curve where you're extremely surface sensitive, and even just adventitious carbon can really muddle up your UPS spectrum. So here's an example that I have. This is a UPS spectrum of molybdenum disulfide crystal as received. And by as received, I mean I peeled off the top layer with some tape and then stuck it in vacuum. So it was a relatively minimal exposure to air. But you can see that this is a pretty broad, featureless spectrum without a lot of detail in it. And when you see that, especially if you have a material that's crystalline or polycrystalline, that's a good indicator that you have too much dirt and junk on your sample. And so how can we remove this? Well, we can use GCIB cleaning. So I did GCIB cleaning at 5 nanoamps and 10 kilovolts to make little clusters. And here we have the green is the as received. The blue is a GCBI clean for 10 minutes, and the red is a GCIB clean for 30 minutes. And you can see that down here in the valence band region, we get structure where there was no structure before. And it turns out this is from the d orbitals in the molybdenum and the p orbitals of the oxygen. And that is the expected structure that we should see for molybdenum disulfide. But it also changes the secondary electron cutoff. You'll notice that the secondary electron cutoff is changing from a larger binding energy to a smaller binding energy, right? It's moving to the right. And that makes sense because where molybdenum disulfide has a work function of around 5.5 eV or so, 5.8 EV, or sorry, has an ionization potential of around 5.5 eV and a work function of around 5 eV. And so as our hydrocarbons have a lower work function, so as we get rid of them, we change the surface dipole, move the vacuum level, and we get something closer to the real data. So those are just a few examples of some things that I commonly see in UPS data and LEIPS data, either lessons that I've learned the hard way or things that are comparable to what customers have come to me and asked questions about. So with that, I want to go ahead and summarize and sum things up. Measuring the ionization potential and the electron affinity is a process that can be easily contaminated by stray fields or surface contamination or heterogeneity. And in order to counteract that, you need to design your experiment specifically around measuring those two properties. So this might be mounting your sample in a different way. It might be thinning it out so you have enough conductivity. But really, you need to tailor your experiment towards measuring those properties. And when you do that, you can have a lot of success and get a lot of cool new physics and good material information that you really can't get from any other combination of techniques.